Hello everyone. So for this coffee and code session, I'm hosting. Yes, Renuka couldn't join today, so she put me in charge. This will be our last session before the summer. So be sure to check out the Slack channel to keep in touch with when is the next session and which will be the topic and the speakers and everything. And but right now I will leave Winnie take over and do his stuff.
All right, cool. My name is Winnie, although I also go by Warren Kretzschmar, which is what I have on my slides. Oh wait, I need to share my screen. Let's do this. All right. Maxime, can you see the screen?
Yes, I can see the screen.
Great. Okay, so I'll be talking about profiling in Python. And since we're all bioinformaticians here, it's really more geared towards bioinformaticians. I'm going to be fairly opinionated, I think, in this presentation. And I think that's definitely true for bioinformatics. But of course, if you're, I can imagine that if other people coming across this presentation on the internet from other fields might feel differently about some of the recommendations that I make. Okay, so yeah, a bit about myself. I am a postdoc at KI right now. I think formally I'm a computational biologist, but I wear many hats. And for the past 10 years, I've basically been writing code in bioinformatics. And most of that work has been on sort of small programs to implement ideas about statistics or to process sequencing data. And so that's the lens through which I have experienced profiling and through which I will describe it today. All right, so what is profiling? A profiler monitors the performance associated with different parts of your code. So the idea here is you would profile after you've established that your code does the right thing. So fans of test-driven development will have all their unit tests passing, and then they start running their code and they go, right, this is too slow, or it's using up too much RAM or too much disk space. So a profiler can help in this situation. And I will be talking primarily about profilers that look at speed or time spent on different parts of your code, but there are also profilers for memory as well. And I think you could probably also profile disk usage somehow, but I'm not sure how that would work. I don't think there's programs for that. So the reason to use a profiler is to figure out where to optimize your code. You've established that it's going slow, but you really want to make sure you're spending your time in the right place. And you might say, hey, but I already know why my code is slow. And the answer to that is no, you probably don't. I mean, you probably don't. So use a profiler, please. Okay. So I think for those people doing TDD and who think about, okay, well, so how, let's say I've done my improvements, how do I make sure that they don't regress over time? And it turns out writing unit tests is probably a bad idea. I've tried it, and the problem with unit tests is that they are fickle. You have to set a cutoff at some point, and then you're always dealing with false positives and false negatives, and it's quite a hassle. So in practice, actually a better approach is to do benchmarking. So you keep track of whatever metric you're interested in, speed, memory usage, on different tasks, and you keep track of them as you make commits to your code base, and then you eyeball them and see how they change. And this is what NumPy and SciPy do, for example. They use a tool called airspeed velocity, which I've also started using, and I can heartily recommend. And I thought we would just take a look at some of the results that they provide. So just to get an idea of what this looks like. So this is benchmarking for NumPy. And the NumPy authors have added lots of tests, and they keep track of the speed. I think it's the speed in this case, but it can be any metric you want to track. And every point here is a commit. And you can see here sometimes there were some commits and then things changed. And when things change, that's the time to go back and figure out, okay, why was there speed up? Let's go profile and figure out what happened. And so this kind of thing is a clear sign that something went wrong. It looks like here there were some improvements done to reduce this runtime. So generally you're looking for sort of spikes and you're trying to get things back to the baseline. Of course, sometimes if we're looking at load times, for example, what was this? I saw some load times. Sometimes the speed things can increase over time, but you can still identify peaks. So I think it's a fairly flexible way of managing the performance of your code and making sure that it doesn't regress. All right. So with that aside, that's to all those people wondering how this fits into their TDD agile process. This is how you would use it. Okay, so I should mention there are two types of profilers. There are statistical and there are deterministic profilers. Those of you coming from C and C++, and probably most compiled languages are well familiar with deterministic profilers. So what they do is they keep an exact track of how much time is spent in every piece of code. And they do this by running lots of other code around it and doing the exact timings. Now that's quite slow because you have not only the code itself that you're running, but you're also running lots of overhead to make sure that you're doing your timing correctly. Then there are another set of profilers called statistical profilers. These are approximate and they are very fast. And the way a statistical profiler works is basically, let's take a sample and see where we are in the stack. All right, let's do it again. And let's do it again. And then you start to build up a probabilist, or you start to build up a sampling profile of where your program is at any point in time. I started using statistical profilers about a year after I started with Python and moved away from C and all those other languages. And I've never felt the need to move away from statistical profilers. So if you're using Python, use a statistical profiler unless you have a good reason not to, would be my advice. Okay, so first up, the keyboard interrupt trick, I guess, or approach, which is ctrl-c. So you can actually run your code and hit ctrl-c and then just see where you ended up. And you get, that's a sample of one, but you can do it a few times and you can get a pretty decent idea of where you are. So the way you do it is you call Python with the -i argument, and then you have to call your program with a library call. I think that's definitely one way to do it. There might be others. And then you hit Control-C whenever you feel like it, and then you look and see where you've ended up. So I have an example provided. I thought we would do some coding to see what that looks like. So my example here is a tool. I should do a little bit of introduction. It's called Streaming PyLaPy. Oops. So I was working with some single cell sequencing data for, recently, and it turns out that some tools I was trying to use required the PyLup format. Now, those of you who've worked with SAMP tools and have run mpylup know what I mean, and I'll give an example of what it looks like. But it turns out that when you're using single cell sequencing, usually you have a little bit of sequencing data from thousands of different cells. And if you do an mpylup across all those, and you have each of those cells in a separate file while you're trying to merge and pile up, that can be quite inefficient. So I wrote a tool that allows you to stream a single BAM file where each cell has a separate barcode or SM tag. Read, what is it called? Read barcodes? I forget. Anyway, an SM tag. And you can do a PyLup that way. So I just threw something together, and it's basically a pure Python implementation of a PyLup. It's not terribly fast, but I think it does the right thing. So I've checked out an earlier version, and I have some example data. So I have a test 11k.bam. This is about 11,000 lines of reads. And if we do, we can first figure out how long it takes to run on that code using user bin time. And let me just make sure that I've got it loaded. All right, I need to activate the environment. Okay, and let's make sure I have the right version. Yep, 052. Okay, so we can call user bin time on as pileup, and it takes as the first argument the BAM file, and as the second argument the sample names of all the tags. And oh, there we go. That's some output. And what we get is a pileup. And so what this is for every cell there are, we first have 3 columns that are the location in the BAM file, and then all the reads that were piled up at that location. And there's 3 columns for each sample. So this is quite an extensive text file if I go to the right here. Most of it is empty, but if you start to see some reads, you get this coding. Oops. Further a bit. Uh-oh. You start to see some reads eventually, I promise, but it does a pile up at every site. And right, so the runtime for the first 11,000 lines, if I just do /dev/null, so I'm piping the output to dev null, should take about 10 seconds last time I checked. And that was a bit slow for me. So I did a bit of work to make it faster. So the elapsed wall clock time is about 10 seconds right here. That's what I usually go by. And so let's figure out where is it slow. One way to do it is, as I said, we run Python -i-m, and then the library name is called streaming py, and the command, the file was called test11kbam, and sample names.txt. So, oops, and I definitely need to pipe the output to dev null, otherwise I'm not going to be happy here. So let's see where we landed. Okay. During the handling of the exception, so the keyboard interrupt happened here, and we have an outfh.write. And we can see here it's 3 tabs. And so this is just a single column that's being written. Yes, so if I recall correctly, what I was doing here is every column that I created, I just made a write call. Turns out that's kind of slow, but let's do it again just to make sure that we, get a bit of a sampling. Oh, still fh.write. Okay, let's do it again. All right, and we're back at outfh.write. So that's 3 out of 3. The maximum likely estimate for the amount of time that we're spending at this particular part of the code is 100%. There, that's your stats. Okay, so we can do it that way, but let's go back to some other options. Turns out the tool that I basically always use is called PySpy. You run your code. You can run PySpy on top of your code, but in practice, usually I'm running some code and I just want to attach to it and I want to figure out why it's going slow. So you search for the PID of the Python interpreter running your code, and then you attach PySpy to the interpreter PID. So let's try that. Okay, so this, you can do it with a regular call. Let's do that first. I think I have PySpy installed already. You can install it with pip. Yep, okay. Oops. What's happening? So PySpy, and you have to it has a few different options. You can do recording, or you can do a top, which is the one that which is what I usually do. Now we don't have to call I don't call the library, but we just call the entry point. And so we're calling spileup. And in this case, I think we don't need this anymore. So PySpy does basically what I did earlier with the ctrl-c, and it just sort of samples and sees, okay, where is the Python interpreter at right now? And all right, that was a short one. Let me run a bigger file. So I took the first 11,000 lines, but test.bam is massive. So we'll just run that, and then we'll have some better sampling. So there's a few different parts. There's this own percentage and total percentage. These percentage values, they bump around, they bounce around a lot. They're just sort of snapshots of the proportion of time that's currently being spent. And then the own time and total time, those are numbers, those are sums of time spent in each line of code. So and own and total is, I can never quite remember. They are basically how much time is being spent just at this part of the line versus everything that's being called by it. So if you have a function call, then sometimes those numbers differ, like here with ingest or add base. So add base seems to be mostly the method call, but ingest, there's a total time and there's an own time. So there's somewhat of a difference. But in practice, what I'm mostly interested in is the line number inside the Python. Oops, okay, didn't like that. Line number 108 inside of streamingpylapy.py. And so let's take a look. Right, I should maybe talk a little bit about why I'm interested in this top line, because, so, I mean, this may seem obvious to many people, but it's worth saying again. If you want to optimize the speed of your code, focus on the things that are slow first, and then go to the things that are less slow. So therefore, you look at the things that use the most amount of time. And in practice, that's also why statistical profilers work really well for this kind of problem, because they represent the parts of the code that are where most time is spent most prominently in this list here. And I could imagine if you were interested in optimizing code that wasn't as important or where not as much time was being spent, then this kind of a statistical profiler might not be as useful. But again, I would ask, why are you optimizing code that isn't taking up a lot of time? So that's something to consider. Okay, so let's take a look at that piece of code and figure out what's being done there. So 108 pi. Please bear with me. I am a new Vim user, so I'm still getting used to it. Right, so this seems to be the line 108, and it is in fact, again, the dot right. So it looks like our two methods agreed on which line is the culprit. That's good. Yes, at this point, we could do a little bit of optimizing, but I think it's sort of beyond the scope of this presentation. I mean, I looked at it and it turns out, yes, doing a write call in Python is actually really slow. It's better to concatenate your strings together a bit before you do an expensive write operation. So that is PySpy. And that's pretty much everything I have found that I need for profiling. I don't recommend using anything else. Of course, if you do need something else, then I should probably point you to the deterministic profiler that is part of the Python library, cprof. You can use that. And there are two profiles that are part of the base library for Python. One's called cprofile and the other one's called profile. But I don't use them in practice because these tools work really well. Oh, okay, I should show one more thing. So you can run the tool directly with pyspy.top, but sometimes you've got a tool that's running in the background or that's already running, and you just kind of want to see, or maybe it's expensive to get running and you just want to kind of dip in and see what it's doing. And PySpy is really nice for that as well. So I'm going to kick off this job in the background because that gives me access to the PID. So now this is running in the background, and I can go into a separate let me just create a little env and activate. Oops. And then pip install PySpy. Cool. PySpy top, and then you do the PID. And now you get to hook into that other Python interpreter and see what it's doing. So this is on Linux, by the way. If you're on Mac, I think you need sudo privileges in order to do this kind of thing, where you hook into another process from a different process tree. But this is really nice if you've got a long-running Python process and you just want to check it out. So if you're on a cluster, for example, you can just SSH into the node and then maybe run some PySpy. OK. So with that, I'll say thanks, and I'll open up the floor to questions.
Okay, so I don't see any question on the chat, and I don't see any question on Slack as well. So I think we can stop the recording now, and I think we can answer the question directly on Slack if there is any, or on the chat if there is any.
Okay.
Does that sound good?
Sounds fine to me.
Okay, thanks again for the presentation. That was amazing. I think, yes, unfortunately, I think for me, I don't use Python that much, so probably they're useful, but that's very good. Thank you.